All right, let's do this. Find the radius and interval convergence for each of the following power series, starting with this first one here. How do I find the radius and interval of convergence? I use the ratio of test. We take the limit. As n goes to infinity, since I do have a fraction, I'm going to multiply by the reciprocal. It'll be x to the n plus 1 over n plus 1 times, flip it, n over x to the nth, right? Okay, cancellation if we can. And we totally can cancel these and just leave an x whenever we subtract our exponents, right? But there's nothing to cancel here. So here, let me just rewrite stuff. Limit n goes to infinity, absolute value of, I'll just rearrange some stuff here. So n over n plus 1, and then we just have an x it's on top, so I'll just put it like right there. That's cool, right? So these are positive. It starts at 0 and then just gets bigger and bigger and bigger. This is always going to be at least, well, there is a case where it's 0, right, if we start at 0. But we're not even close to 0. We're going to infinity, so this positive number, absolute value doesn't affect it. And so I can take it out of the absolute value. Okay, what is going on? Oh. Hold on a second, folks, technical difficulties. I can take it out of the absolute value, get n over n plus 1 times the absolute value of x. You can't take this thing out because, like, we don't know what x is. We're trying to figure out what x can be. It could be positive numbers, could be negative numbers, whatever. Okay, whenever I take the limit now as n approaches infinity, this is infinity over infinity, which you can use the L'Hopital's rule on, but I'm not gonna, because use the pre-cal rule, this to the first power, this to the first power. This is just gonna go to the limit, the ratio of the coefficients here, which is 1 over 1 here. This goes to 1, that goes to 1, and so the value of this limit is just the absolute value of x. And if this thing is going to converge, the absolute value of x needs to be less than 1. So I'm going to pause right here. When we define the radius of convergence here, it's got to look like this. Absolute value of x minus c, where c is your center point, and that's going to be less than some sort of finite number here. All right, so match stuff up. What is our center point for this thing? Well, this is x minus a whole bunch of nothing. The center point is 0, and we can see our finite number here is 1. And so this guy right there is our radius of convergence equals 1. All right, and now we're just going to keep going here because we haven't found our interval. We'll just have to apply like some algebra to this thing, and this radius convergence is going to surround our center point, which is going to be -1 is less than x, which is less than +1. And remember that the radius test, if we were to stick in 1 here into this limit, I can stick it in here, stick it in over here, it won't even matter. The limit is going to be equal to 1. Ratio test fails, so we need to check 1, and we likewise need to check -1. Let's just do those one at a time. We're going to check the endpoints. Endpoint convergence? Maybe that should be plural. Here, let me make that plural real quick. Starting with x is equal to -1 here. So if x is equal to -1, we go back to our original power series and just stick -1 in here. So we have sum n equals 0 to infinity. And I just have x to the nth, so our x is a -1 to the nth power over just n. Hey, does that look familiar? That is the alternating harmonic series, which converges. Alternating harmonic. If you can't read that, and I can hardly read that, that says harmonic series, which converges. It doesn't converge absolutely, it converges conditionally, but at least it converges, which means that we get that endpoint. How about x is equal to +1? Okay, so again, rewrite your series with x equals 1 in the place of x. No, that's a 0. So I have 1 to the nth power over n, 1 to the nth power doesn't even matter. That's just going to be a 1. And now this one is just the regular harmonic series, which diverges. That means that we don't get this endpoint. And here is our final answer for our interval of convergence. We got the left endpoint, but we didn't get the right endpoint. This is interval of convergence. Okay, let's do another one here. Here's the second one. I'm going to take the limit as n goes to infinity. I'm going to have to multiply by the reciprocal kind of thing again, so negative 1 to the n plus 1, x plus 1 to the, don't forget your 1, to the n plus 1th power over 2 to the n plus 1 power times reciprocal 2 to the n over negative 1 to the n, x plus 1 to the n. Okay, cancel. Cancel stuff. Like this guy in this guy leaves just a negative 1, which with the absolute value is just going to go away. All right, and then how about these two n's? So the 2n plus 1 that's on the bottom, it's a little bit bigger by a factor of 2 when you subtract your exponents. And then likewise, these will cancel out, leaving just one factor of x plus 1. All right, let's make this look a little bit more elegant so we can see what the heck is going on here. Okay, so we have the absolute value of negative 1, which really doesn't matter. X plus 1 is the only thing left up top, and then on the bottom we have the number 2. Okay, all right. As far as this goes, the only thing that really needs the absolute value is the x plus 1, because this negative 1, absolute value, that's just 1, and then the 2 is already a positive number. Maybe I rewrite this one more time. This is just the absolute value of x plus 1 over 2. If you take the limit as n goes to infinity, there's no n's. That means that the limit here is just equal to the absolute value of x plus 1 over 2. And this is only going to converge if this quantity here, by the ratio test, is less than 1. Does that mean that the radius of convergence is 1? No, it's not. Because if I come back over here, remember this is what the radius of convergence absolute value inequality looks like. It has to be just x minus its center point. Hey, where's this one centered anyway? At 1? No, at negative 1, right? Yeah, so I have to get rid of this 2. I have to multiply this 2 over here. So I have the absolute value of x plus 1 is less than 2. Now we have our radius of convergence. Radius is equal to 2 in this case. So you can see it's not always going to be 1. All right, and then get rid of your absolute value bars by rewriting this between a negative 2 and a positive 2. And then subtract 1 everywhere. We get a negative 3 is less than x, which is less than 1. All right. So here is almost our radius, our interval of convergence. We just have to check a negative 3. We have to check a 1. We have to check our endpoints. Endpoints? Question mark. We'll start with the first one here. By first, I mean negative 3. So again, back here where there is an x, we'll stick in a negative 3 and see what happens. So we have sum n equals 0, infinity. We have the negative 1 to the nth power. And then what else do we have? We have negative 3 plus 1 to the nth power over 2 to the nth power, I think it was. Yeah, it was. Okay. All right, and then just rewrite stuff so that we can simplify and see what kind of series this thing turns out to be. Okay, so negative 1 to the nth, that stays. This becomes a negative 2 to the nth power, but I can rewrite that as negative 1 times 2 to the nth power over 2 to the nth power. And then we can rewrite some more, -1 to the nth power. And then, oh, I just recorded that. Split this thing up as -1 to the nth and 2 to the nth power. -1 to the nth, 2 to the nth. Does that go on the outside of the parentheses? Come on, yes, we'll make it to the... Oh, guess what? Look what happens here. Cancel, cancel. And then you can combine these two things here. That makes that -1 to the 2n power. Why is this red? Come on. This one here. Sum of just -1 to the 2n power, which is basically the sum of just ones. And so the sum of an infinite number, because this is to the 2n power, so it's always going to be a positive number. It's basically 1 plus 1 plus 1 plus 1 plus, that goes to infinity. This diverges. Hey, it looks like we ran out of room here. My gosh, that's one problem. Am I right? All right. So we don't get that endpoint. Well, maybe we get the other one. So the other endpoint was the number 1, right? So plug in a number 1 for our sum. N equals, I was about to make that an and symbol again because that's what I do. -1 to the n. We have a 1 plus 1 to the nth power. Is that right? I don't remember. Yeah. Over 2nth power. And it looks like the same kind of thing is going to happen, almost, right? Because we have now the sum -1 to the nth. 1 plus 1 makes that 2 to the nth over 2 to the nth. These guys cancel out, and you are just having -1 to the 0 power, so you get 1 minus 1 plus 1 minus 1, which diverges. Okay, what does that mean? That means we don't get that endpoint either. And our final interval of convergence is the one that we started with. Wow, all of that work for nothing. Well, not for nothing, because we at least were able to eliminate the fact that it converges at its endpoints. Okay, so this is our interval of convergence. All right, and then we just have one more, folks, and this is going to do the lesson. Pardon me. All right, let's take the limit, shall we? Limit as n goes to infinity. Absolute value x to the n plus 1 over n plus 1 quantity squared, multiplied by the reciprocal here, n squared over x to the nth power. Okay, we're in good shape. Cancel stuff. So subtracting the powers of x, it's bigger on top, so we just have a power of x there. And then unfortunately, there's nothing that we can do here. However, they are positive because we're squaring them, and they're going to be positive anyway. So they can come out of the absolute value, and then it becomes the limit as n goes to infinity of n squared over n plus 1 quantity squared. But the absolute value of x, or the x thingy, has to stay in the absolute value symbols. All right, and then we can see that we have a squared over a squared. We take the limit as n goes to infinity. That's just going to go to 1. And the value of the limit then is just equal to the absolute value of x. And it will converge by the ratio test as long as this is equal to 1. And our center point here, you can see, is 0. And this number over here is the radius of convergence. All right, and then as we've done before, we get rid of the absolute value symbols as -1 is less than x, which is less than +1, and we'll have to check the endpoints. If you cannot read that, it says endpoints, not end points. Just take my word for it. Let's check -1 first. We have the sum n equals 0 to infinity of -1 to the nth power over n squared. All right. I can do a couple of things here. One of which is this thing looks like a power series here. And if you were just to take the absolute value of this guy, take the absolute value of this, then it would be just 1 over n squared, which is a convergent P series. P is equal to 2, so this thing converges. And it actually converges absolutely because I took the absolute value of it, which means that the original one also converges. Right? Yeah, I mean, you could apply the alternating series test if you want to, but all this means is we get the left endpoint. Hooray! I wonder if we get the right endpoint. I have a pretty good feeling about it. X is equal to positive 1 gives us the sum from n equals 0 to infinity of just 1 to the nth power over n squared. 1 to the nth power is just going to be the number 1. And now we do have, in fact, the same thing that we had after we took the absolute value of the other one. We have this convergent P series where P is equal to 2. 2 is bigger than 1. It definitely converges, which means that we get the other endpoint as well. We get both of them. It's a happy day. All right, so this, of course, is our interval of convergence. Interval of convergence. The domain of this thing, if it was taken as a function defined by some sort of power series, which brings us, folks, to the end of our lesson. We were able to find both the radius and the interval of convergence for a power series. A power series you can think of as a whole entire collection or perhaps a function of series. And we want to know where do all of those series converge, and that is the interval of convergence. We find that interval of convergence by just simply applying the ratio test and seeing where that ratio is less than 1. Ordinarily, that less than 1 thing is the radius, but it's not always just 1. It could be some other finite number. And since the ratio test fails at r equals 1, or when the absolute value is equal to 1, we have to test the endpoints, don't forget. All right, that brings us to the end of this power series lesson, but there is a whole bunch more stuff on power series. Like, for example, if this thing is a function, then maybe we should be able to take derivatives of it, take the antiderivatives of it, and do regular calculus stuff on this new kind of function defined by a power series.